We're going to just do a little bit of this. Kind of like to go till about, I don't know, 2:15, 2:30, take a break, 15 minutes, take a test. I'm going to see in that time whether or not there's an open classroom where you can actually sit at desks and have your feet flat on the floor and not be twisted sideways, that kind of stuff. But there's a chance that we won't find that. This is probably the busiest time of the week. Mondays and Wednesdays afternoons, Tuesday, Thursday afternoons, the busiest time of the week for classroom. So they're usually, usually busy, but hopefully we can find some. So let's talk about chemical equations. This is an example of a chemical equation. There's different parts to it, so this is kind of the anatomy of a chemical equation. It has a reaction arrow. So that's what this guy is. That's the reaction arrow. I think most of you knew that. But there are different ways the arrow is drawn. It doesn't really mean anything different for what we're doing this chapter. Sometimes you'll see an arrow drawn like this, right? That means it's what's called an equilibrium reaction, but really it's still a reaction arrow. Right? It separates the sides of the reaction. The left side is called the reactants. Right side is called products. So just curious, for how many of you is this part just completely new terminology? Don't know it at all. Everybody's kind of familiar? It's brand new to you? Okay, so I'll make sure I try to explain what's going on here. So these are the things here that you would be putting together to make something else. It's what you're bringing together. It's the stuff you started. So it's with a starting point of the reaction is the left-hand side. So that's the reactants. The products are what you're going to get after the reaction takes place. You know, and it's trivial for us to say the products are things produced by the reaction, but it sometimes doesn't click. These things don't exist before those things. Right. Here's another thing to think about. If at let's say in this reaction, the way this is done, if I sodium sulfate on the left, if I used one sodium sulfate, like compound, right, I would get 4 carbon monoxides out. So it's also telling us, in addition to telling the reactants and products, it quantitatively tells us like how much reactant is used to make how much product, or how much reactant is used for every other reactant. So for example, this is the material balance. The numbers, those represent what are called stoichiometric coefficients. And they represent the proportions in which the reactants and products are used. And those numbers are locked together. That's just the way it always occurs for these things. So if I used up 4 carbons, right, I would produce 1 sodium sulfide on the right. If I used 8 carbons, I'd have 2 sodium sulfides there, AUSs. They just have to go in those proportions like that. Other things that are listed, and that's probably in terms of like generalities, that's probably one of the most important things we get out of balanced reactions. The other things that we have listed in the chemical reactions are the states of matter. The states of matter are S, solid, L for liquid, G is gas. So those are the physical states of matter that we talked about when we talked about, matter and its changes earlier in like chapter 1, I think it was. Yeah, chapter 1, right? But then there's also the other state of matter that's important to know is what we call AQ, and that's aqueous. It turns out, and I mean, at this point, most people, I think hopefully understand what aqueous means. It just means it's dissolved in water. And so water is the solvent, like it's a solution. Water is the solvent, and that substance is dissolved in water. It turns out in other, if water's not the solvent, sometimes they'll put another term there for what the solvent is. So like if things are dissolved in liquid ammonia, it would actually say negative. It would say something else. But for general chemistry, what we're doing here is Chem 1A, Chem 1B. It's almost all aqueous reaction chemistry, so that's kind of the one we focus on. It also includes in the chemical reaction conditions. So you'll see things like this. This means heat. That just means get it hot. It's in a beaker. You warm it up. The lab for next week, we're going to put methanol and iodine and zinc together, and we're going to heat it. So you would actually put a little delta there and say we're heating it. And we'll produce a product out of it. You can also specify temperatures. So if it's at a specific temperature, you can put temperatures. If you're familiar with the term pH, pH is often included on that arrow. The conditions in which you need to have to make the reaction go, those are listed on the reaction arrow. Okay. I've only listed the one here. The ones you're primarily concerned about at this point are just heat. If it has to be heated, it'll have a triangle on it. That's what you do with it. Unfortunately, that doesn't tell you how hard you heat it. There's some solvents that we use, like in organic chemistry. If you get them up above 180 degrees, they'll just ignite. Oh, that was too hot. They didn't tell me that I shouldn't heat it that much. So we're going to write some chemical reactions. And this is what a problem might look like. This solid magnesium hydroxide can be synthesized from the reaction of solid magnesium nitride to water vapor, and ammonia gas is produced as a byproduct. So first thing that you want to do is read through and identify reactants and products. Okay. So we're going to identify. This is what I do. The second thing that we're going to do is we're going to write down chemical formulas. And the third thing we're going to do is we're going to balance it. I haven't talked about that yet. We have a lot of slides on balancing. But balancing is where we get those numbers that were the stoichiometric coefficients in the chemical reaction, where we know the ratios of things that are used and produced. So we're going to work on balancing reactions as well. This will give us the coefficients. Okay, so let's highlight some of these things. Solid magnesium hydroxide can be synthesized. What does synthesized mean? You may know? Could be a new word for you guys. I'm not. It means to, it's made. Yeah, synthesize means to make. So what does that sound like magnesium hydroxide is then? It's a product, yeah. Yeah, magnesium hydroxide can be synthesized. So this is a product. This is a black highlighter? What's this? This is just a black pen. I thought I had another highlighter in here, but maybe I don't. Okay, I can make another highlighter real quick. Oh, actually, you know what I'll do? I won't make another one right now. I'll just... So magnesium hydroxide, and then I have what's this guy? There we go. That looks better. What else gets produced? Ammonia gas. So a byproduct is something that's produced as part of a reaction, but it's not usually what you're interested in. It's not what you're trying to make. Usually in a chemical reaction, you're trying to make something, and a lot of times when you make something, you also make waste products that you don't care about. Okay, so then what else do I have? I have to do my reactants, right? So my reactants will be this. So my reactants can be synthesized from, right? So that means I'm going to make it from, it's going to be this guy and this guy. So now we need to write the formulas. So for my reactants, magnesium nitride, I have to figure out what it is. It's Mg and it's N, because it's IDE, right? IDE is monatomic. What's nitride's charge? What's nitrogen's charge, really? 3 minus, yeah? So 3 minus, and this is 2 plus. So the formula for magnesium nitride is Mg3N2, right? And that's going to be a solid, right? So I'm going to make a little note of that there. And then, let's see, the other reactant is water vapor. So that's going to be H2O. There's no figuring out for that one. You're just supposed to know that, right? So, and then the state for that would be, what's the vapor? Gas, that would be G. And then for my products, ammonia is another one of those you should have memorized. It's NH3 gas, like that. And then, let's see, what else? Magnesium hydroxide. So it's Mg2 plus again. And it's OH minus. So what's that formula going to be? MgOH2, yeah. Like that. Yeah, that's a G. I thought you said that was the 3 by the NH3, and I'm like, yeah, that's a 3 by the NH3. I got confused for a second, sorry. My bad. It's the ears. I'm just going to keep blaming my ears for that. Does it give a state for that? It's a solid, right? It's very beginning. Magnesium hydroxide. This is my solid. All right. So now what I have to do is I have to write everything in a chemical reaction, reactants to products. So I have magnesium nitride, Mg3N2 solid, plus, let's see, water vapor, which is H2O gas, a reaction arrow, and I'm going to have my products, which are going to be, oh, I have backwards, huh? No? Magnesium hydroxide, MgOH2. And that's a solid plus NH3. And that'll be gas. At some point, you won't have to do all this writing. You'll just say, oh, that's that. Just write it down. But if it's the first time you're doing it, it's very helpful to write out figure out what the reactants are, what the products are, write their formulas, and then put it all together. Okay? So that's the chemical reaction. It's just not balanced. And the question is, how are we going to balance it? I'll show you really quickly how I do this one. But then, yeah, we'll work it out on here. So I already sort of pre-did the work here, and I wrote out the rules on the side. And then we'll kind of walk through it. It says, start with the compound that is most complicated. And generally what I'll do is I'll circle that. And then I'm going to tell you, they call this balancing by inspection. So I'm going to do this. I'm going to start with that, and I'll circle it on the reaction. This is already a bad instruction, but what's complicated? Balancing by inspection is just like intelligent guessing. You just start with something, just to see if it works. Okay. So what I'm going to say is the most complicated thing is probably the Mg3N2 because it has like 5 different things in it. So that's what I'll start with. And then what I'm going to do is I'm going to balance everything on the other side of the reaction that's in this compound. So everything that's in Mg3N2, magnesium nitride, I'm going to balance those elements on the right-hand side. Okay, so balancing means you have the same number. That's all. So how many magnesiums do I need? 3s, right? So what I'm going to do is I'm going to add the number 3 here. That gives me my 3 magnesiums, right? And then for the nitrogens, how many do I need? 2, so I'm going to multiply this one by 2. Like that. Okay, so that means that's we're halfway done. That means that everything in that compound is balanced with everything in that compound. The only thing that's not balanced is the other stuff. Okay? And it doesn't matter like which element you start with. You're always going to come to the same balanced equation. It's like like in math, you have to solve an equation. There's like one solution to the equation. This is what this is. There's just one solution to this. So let's tally things up real quick. All right. I have how many oxygens here? I have 3 oxygens, right? Because I'm looking at, sorry, I have 6 oxygens. So I'm going to look at these guys here. There's 2 here times 3, so I have 6 oxygens on this side. And then I have how many hydrogens? I have 2 times 3 here, right? So that gives me 6 plus 3 times 2 here, which gives me 6. It is 12. Yeah, no, it's 12. I just didn't want to just like, this is 6 oxygen. That's the letter O. 6 plus 6 hydrogens. So I have 12 hydrogens like that. So how many waters do I need? You see how many oxygens? So the way I'm going to balance these guys, if there's only one thing left, it has to all be balanced by that. So how many oxygens are on the right? So how many do I need on the left? So what do I have to multiply by? There we go. Just like that. Now, there's different ways to do this. Okay, the other way to do this, just to show this to you, is to look at the elements and just go left to right and say, I have Mg, I have N, I have H, and I have O. And then to do inventories on the left and the right-hand side. But what I would always do is I would always do that circled green step first, and then I would just make the inventory for the rest of the stuff that's not balanced. Because if you do everything, and then you have like 4 elements and all these numbers, if you've already balanced 2 of the 4, then you just do the 2 that aren't balanced. That's a much cleaner picture of what you need to do. Okay? Now, just as a side note, start with elements that appear only in one compound on each side. Like, it would have been bad for me to start with like H2O to try to balance, because there's H's in magnesium hydroxide and H's in NH3, and now you have 2 variables you're working on the right side trying to balance one variable on the left side. It's just much harder to do. So if you start with things like magnesium nitride, where magnesium is one element on this side and nitrogen's in one compound on this side and nitrogen's in one compound on this side, it's much easier to balance it that way. Okay? And the last thing is, if you have something that's a pure element like oxygen or nitrogen or fluorine, chlorine, any of those like diatomics or just iron, leave those to last because you can always put a number in front of it and balance it. It's really easy to do. Okay, so let's practice this. I don't know how many of these I have. But I have a few. So go ahead and try it. Decide what you're going to start with. And go. Question, I can come by. I'm going to go check with Austin to see if we get those we need to do. Yeah, there's nothing open. Okay, so let's see where we go. We're going to be examining here. I'll try to work on something and see what else is available during this semester. But the classrooms we usually use are going to tear them down. So that's where they're going to put the new building. So they're offline, so they may not have power or anything. Okay, so what did I start with? Yeah, see, it's not too bad, huh? And so then what do I have to do? How many aluminums do I need? 2. Okay. And then how many oxygens do I need? Okay. So then, so now I've done the aluminum, I've done the oxygen, so I need the H, right? And the Cl, so this is what I was talking about. Just do the things that are left over. And then how many hydrogens do I have on the right side? How many chlorines do I have? Okay, so that means, like, I only have the 1 here, so now it's 1 and 1. So what do I need? 6. Like that. A lot of times people will not do that first step, and then there's this big long list of elements, and then you've got to go through all these lists, and they get really confusing, and there's calculations involved, and it's just not fun, but that's how you do that. Here, let's do this one. This ethanol burns, combustion, is a type of reaction you'll need to know, to produce water vapor and carbon dioxide gas. Right? The balanced chemical reaction. So, first of all, we have to know what ethanol is, right? So how many carbons in ethanol? Did I teach you mother eats peanut butter? Mother, methyl, eats ethyl, right? Peanut butter, propyl, butter, and butyl. So, yes, 2. So mother eats peanut butter. So its formula is actually C2H. I'll write it as an alcohol, right? Alcohols have an OH functional group on them. Plus, there's no states on that, unfortunately, but it's a liquid. So I'll put a liquid state in here. Plus water vapor. Oh, burns. So combustion requires oxygen. So one of the things you'll need to know is that it's O2 gas. And then it produces water vapor, which is one headed arrow. H2O gas. Right. And, what's that? Oh, I'll get to that in a second. And then CO2, and that's gas. Yeah, so the reason I put the O2 is because when you burn stuff, it requires oxygen. So a combustion reaction, by definition, is very basic. Combustion reaction uses oxygen. So if you have the combustion in anything, you have to have oxygen and O2 on the reactant side, and then whatever the oxide of the product is, and then we don't write the heat, but we'll learn how to deal with heat. It produces heat energy. Yeah, so combustion uses oxygen. And that means it's a reactant. Okay, just again. Okay, so we have to balance this. What are you going to start with? No. Which substance do you start with? Yeah, most complicated. So that looks like this, right? Yeah. All right. So that's where we're starting. Go ahead and work from there. You're trying to do it all in your head, aren't you? Like, I don't want to write this down. I just want to do it in my head. I know you too well. And we'll do the number of O2s you need together. I'm going to just start writing some stuff up here. Don't try to do the oxygens yet. We're going to just deal with the carbon and the hydrogen. I'll tell you why in a second. So did you get these numbers like this? I got a 3 and a 2, right? This is the reason you don't do oxygen, because oxygen is in everything, so you're going to have to figure that out separately, okay? So the things that are only in one, like the carbon, is only in the CO2. The hydrogen in that compound is in the H2O. That's easy to do. Now we have to do the oxygen. We'll do the inventory to do that. Okay. So here's what we're going to do. The only thing that's left is the oxygen, right? So I don't need to write all the other stuff down. It's all balanced. Huh? So this is how many oxygens do I have on the right-hand side? I have 3 and 4, so that gives me 7. And I literally will, when I do these, I write them out. I do each one separately and then I add them together, just so I don't. Because like Eric was trying to do it in his head right now. He was trying to add you were trying to add the oxygens together. Yeah, I could see it in his face. He was in my 3A class, and I can tell when he's thinking about oxygen and all these things. He sits there way too long and just looks at it, and I'm like, oh, he's just trying to do it all in his head. Okay, so then what you're going to do is say, I need 7 oxygens. Now, there's 1 already here, right? And I don't want to mess with that one because that's in a compound that's already balanced. So how many more do I need? 6. So how many O2s do I need? 3, like that. Okay. So you see the process I did there? This was already balanced. So don't change after balancing C and H. And then you just have to figure out how many more you need. And since oxygen comes as 2, okay. So what does a balanced reaction tell us? I just feel like I'm obligated to say this part. A balanced reaction shows the law of conservation. But it also shows us like the ratios in which reactant products produce because of the consequences of conservation events. So for like methane, there's 2 oxygens get used, 2 O2, that produce CO2 and 2 water. You can literally, if you think about what these things look like, right? There's 1, 2, 3, 4 hydrogens here. There's 1, 2, 3, 4 hydrogens here. How many oxygens do I have? I have 1, 2, 3, 4, and there's 1, 2, 3, 4, and there's 1 carbon here. There's 1 carbon there. All right, so you literally are counting exactly. All the atoms on the left are represented. But this is going to be important because this will allow us to be able to calculate how much material of a particular type gets produced from a reaction. Fixing these ratios allows us to make those kinds of calculations. Okay, so I'm going to show you how I use this. This is how you should use this. These are mole to mole conversions. So if I have 13 moles of oxygen, right, I want to know how many moles of CO2 are produced. So you go like this. You say there's 13 moles of O2. And then what I need is the mole ratio from the chemical equation. So I want to know the moles of CO2 from the moles of oxygen. And if I do that math, I'll get moles of CO2. But I'm missing some things here, and I'll show you what they are in a second. But you guys get the premise. The moles of O2 will cancel. I'll be left with moles of CO2. That mole ratio comes from your chemical equation. So if you look at the balanced chemical equation, it actually says 1 mole of CO2, that's the one that's here, right, is produced from 2 moles of O2. That's my mole ratio. So I end up with 6.5 moles. So we use the balanced chemical equations, the stoichiometric coefficients, as conversion factors to convert from one kind of substance. and just set it up so the units cancel. All right, for your calculating pleasure, you do this one. How many moles of water must be consumed to produce 7 moles of ammonia? Again, mole to mole conversion. I'll start writing it up here, and then we'll talk about it if you have questions. Okay. Yeah, so is that what you got? Yeah, so what I did was in my head, or actually I did it in my head, but I wrote it out for you. I wrote out 6 moles of water. I knew I needed to go from water to ammonia because I saw that in the question. It said 6 moles of water, 6 moles of NH3, that gives me my mole ratio. I'm starting with moles of NH3, which I did not write the word moles. Moles goes in here. Is that 21 moles of, oh yeah, I canceled it out. That's what I get for not canceling units out. I just wrote something down. Nice. 21 moles each. Yeah, so then I set it up so the units canceled, and then I just did the calculation. Pretty straightforward. All right, that's where we're going to stop because the next part's a long story. It's called My Bicycle Factory. And we're going to talk about, this is where I introduce the terms that go along with balanced chemical reactions and their calculations. We'll take like a 15-minute break. You can go to the bathroom, do whatever you need to do, get a drink of water, caffeine, cry.